Hello everyone and welcome back to another video. Today we're going to talk about angles in standard position. Now before we get started, let's go ahead and make sure that your calculator is in degree mode. The alternative is radians, but that's going to be for Math 30-1. So what we're going to make sure of is every time that you or your teacher has reset your calculator, we're going to switch our calculator into degree mode because the default setting for calculators, or graphing calculators at least, is going to be in radians. So starting off with the TIs, we're going to click into it. We're going to hit the mode button, which is right here. And then after that, we're going to we're going to go down, and you can see here that we're currently on radians. So we're going to hit the right arrow, press enter, and we can see now that we are highlighted on degree. You can press clear to go back. And now we are on degree mode. Going to your Casio calculator, let's go ahead. We're going to hit shift, then menu. And you can see here by default, we are looking at an angle that's going to be measured in radians. So we're going to scroll down and we're going to hit F1, at least on my calculator, to go to degrees. Some of you guys might be wondering, well, what's the big deal about having your calculator in degrees versus radians? Well, one way that we can just show the difference between the two is if I were to go to sine of 60 and I press enter, we can see that we get 0.866. If I switch my calculator back into radians, so let's go ahead and do that. Switch back into radians, and we do the exact same thing. So sine of 60. You'll notice that we get a completely different answer. Okay, and again, for the radians here, we're not going to worry about that too much. We're actually going to be looking at sine of 60 later on in the video, but you can see that there is quite a substantial difference in terms of what the output is. So before we get into the new 20-1 content, let's go ahead and review some of the content from previous courses. Looking at our two main tools for dealing with triangles, we have SOHCAHTOA and Pythagorean theorem. So once again, SOHCAHTOA, we can rewrite like this. So we have SOH, and then we have CAH and TOA. And this is really just an acronym to help us remember our three primary trigonometric ratios. So we have sine, which is opposite over hypotenuse, cosine, which is adjacent over hypotenuse, and tangent, which is opposite over adjacent. Now, in terms of the Pythagorean theorem, it's going to be a squared plus b squared is equal to c squared. So if you have two sides, or the sum of two squares is equal to the last side, we know that this last side is going to be the hypotenuse. Now, if we look at this question, we're being asked to find the length of d to e. So that's going to be this side right here. So let's go ahead and call that x. If we're using the Pythagorean theorem in this case, we know we have two sides that we're going to use. So once again, we need to figure out which tool we need to use. Here we have two sides. So the Pythagorean theorem has three sides. With any of your trig ratios, you have two sides plus an angle. Here we don't worry too much about the angle, so we know we're not going to use any of the three primary trig ratios. So moving into our formula, let's go ahead and rewrite it. So a squared plus b squared is equal to c squared being our hypotenuse in this case. So we have our two non-hypotenuse legs of our triangle. So it doesn't really matter which one is a, which one is b. So we have x squared plus 8 squared is equal to c squared. Let me change my color here. So we have x squared plus 64 is equal to, I missed the 20. So is equal to 20 squared, which is going to be 400. We're going to subtract 64 from both sides. So we get 336 is the same thing as x squared. And square root on both sides, we have x is equal to plus or minus the square root of 336. And because we're looking at a length, we know that it's going to be a positive length. So it's going to be the square root of 336, which is roughly about 18.3 centimeters. Next, we're going to look at the measure of angle F. So let's start by labeling our different sides. So if this is my reference angle, the point of where we're starting in our triangle, directly across from angle F is going to be my opposite side. Our hypotenuse is across from the right angle, so I'm going to go ahead and label that. which means that our adjacent side is going to be that 8 centimeters there. If we were only looking for the measure of angle F, I'm going to use the two sides that are given to me so I know that I'm using the correct numbers. So we can start off by saying that we are going to look at the adjacent side and the hypotenuse. And because those are the two sides we're working with, we're going to use the cosine ratio. So cosine of angle F is equal to the adjacent side divided by my hypotenuse. Since I'm looking for cosine of F, we're looking at the adjacent side, which is 8 over 20. And in order to isolate F, I want to get rid of that cosine function. So in order to do so, we're going to take the inverse cosine. So the inverse cosine of the left-hand side just leaves us with F. And on the right-hand side, we now have the inverse cosine of 8 over 20. I'm plugging that into our calculator. We end up getting F is equal to about 66.4 degrees. So once again, on your calculator, if I were to pull this up here, let's punch in second cos, and I'm gonna put 8 over 20 into the calculator, and we get that 66.4 degrees. You can pause the video and try out these two questions underneath, and then unpause once you're done to check your work. For these two questions at the bottom, we're going to solve for all of the missing measures. So here, let's highlight some of those things we're looking for. So we're looking for angle A. We're going to try to find first. So angle A is equal to something. We're going to find out side A to C. Let's call that X. And last but not least, we're looking for side AB, and let's call that one Y. So let's start off with angle A. We know that in a triangle, there's going to be 180 degrees. So that means when I add all three angles up, we're going to end up with 180. So that means that angle A plus B plus C has to equal to 180. And substituting in all of my different angles here, I have A plus, and we know that angle B is perpendicular. So that's going to be 90 plus angle C, which is 42, has to equal to 180. So I have A plus 132 on the left-hand side. And then we're going to subtract 132 from both sides to isolate for A. And we end up getting A is equal to, 48 degrees. If we were to solve for side X, what we're going to do is use one of the trig ratios. So since our reference angle is angle C, we'll start off with that. I'm going to call this my opposite side. This is my hypotenuse, and this is my adjacent side. So looking at a couple different things that we need, we know that we have the adjacent side that we will need. And since we're looking for the hypotenuse, we're going to use adjacent and hypotenuse, which means we are utilizing the cosine ratio. So remember that cosine of some angle is equal to adjacent over hypotenuse, and then substituting in all of our known values. So cos of 42 is equal to 16.39 divided by x. To get x by itself, I'm going to multiply x onto both sides. So that means I have x times the cosine of 42 is equal to 16.39. And then dividing both sides by cosine of 42 gives me x is equal to 16.39 divided by cosine of 42. I'm plugging that into my calculator. I end up getting about 22.1 centimeters. Now moving on to side Y, we're now looking for the opposite side. So again, using the side that we know for sure is correct, we're going to use the 16.39. So we're now looking at adjacent and hypotenuse, which means that we're using the tangent ratio. So tangent of angle C is equal to opposite over adjacent. And then substituting in all of my known values, tangent of 42 is equal to y over 16.39. Multiplying 16.39 up onto both sides means that I have 16.39 times tangent of 42 is equal to y. And then we end up getting y is equal to about 14.8 centimeters. Here you can pause the video and try out the second triangle on your own. Remember, we're going to look for three things. We're going to look for side X here. We're going to look for angle X and then angle Z. So the three things, X is equal to something, angle X is equal to something, and angle, sorry, not Y, angle Z. So we got angle X and angle Z is equal to something. So pause the video and unpause once you're done to check your work. To start us off here, we're going to look at some basic vocabulary to help us get going. First off, we have what we call an initial arm. So let's go ahead and draw the initial arm here in, let's say, red. And this is going to be the arm that lies on the positive x-axis, which is going to be where our angle is going to start. So here is my initial arm. And the initial arm is really just a ray. Remember that a ray is where we have one fixed endpoint, and we're really just extending infinitely in one direction. Next, we have what is called the terminal arm, and it's going to be an arm that meets with the initial arm, which is the red line, at the origin, which is at 0, 0, to create some sort of angle. So let's go ahead and draw my terminal arm. And we'll see that we create some sort of angle here. Let's say that that is maybe 120 degrees. So now we have our initial arm and terminal arm. What we're going to do next is define what an angle in standard position is. So we have an angle formed by the initial arm and terminal arm. It does become a bit more nuanced than that. So standard position is really just our default position to measure an angle. Now you might be wondering, well, what does an angle in non-standard position look like? Well, we can see that our initial arm here starts at the origin, and it's the same thing with our terminal arm and meets the initial arm at the origin. Something that's not in, or that is in non-standard position might look something like this instead, where the meeting point that creates the angle is not right at the origin. Or you could have something that looks even weirder. We could have something that looks like this. And maybe what we'll do is we'll have the initial arm actually be up there. So both of these would be examples of angles in non-standard position. Again, not something that you need to worry about in Math 20-1. Next, we're going to talk about the reference angle, which is just an angle formed by the terminal arm and the closest x-axis. So for us in this particular example, this right here, let's call that theta, and let's make that our reference angle. So theta is just a variable that represents an unknown angle, kind of like x or y. But when we're using trig, we typically utilize Greek letters like theta, alpha, or beta. Another example of a reference angle might look something like this. So again, starting off with our initial arm, and then let's do our terminal arm down here. Our reference angle, once again, is going to start from the terminal arm and going up to our closest x-axis. So this purple angle right there is going to be our reference angle. So a few things that I want to add as well. If we have a positive angle, we are always going to be moving counterclockwise. If we have a negative angle, then we're going to be moving clockwise. So let's say, for example, if we were moving the opposite way, and let's start with our initial arm here, and we are now moving down this way. We're moving, maybe I'll make that a little bit longer. We're moving down this way towards the terminal arm in this direction. This is, or this could potentially be negative 120 degrees. So looking at our examples here, please excuse this random symbol there. That should really say 150 degrees, so just ignore that for these other two examples. We're going to draw our angle in standard position and then state the reference angle. So looking at our Cartesian plane, 150 degrees, starting off with our initial arm, just right there. And then our terminal arm is going to be somewhere in this quadrant here. So drawing my angle, we know that this is 150 degrees. And then we're going to look at the reference angle. So the reference angle is going to be this angle right there. Now to measure the reference angle, we know that going or starting from here, we go up to 90, then 180 degrees, 270, and then all the way around for 360 degrees. If we've gone 150 degrees so far, that means that we only have 30 degrees or 180 minus 150 to give us our reference angle. So our reference angle in this case is equal to 30 degrees. And we get that by saying 180 minus 150 is equal to 30 degrees. Here you can pause and try out the next 3 examples on your own. Here on this page, we're going to play around with the idea of reflecting our angles in some of the axes to figure out what our angles in standard position are going to look like. So starting off with 75 degrees, we're going to reflect the angle in the y-axis. So here, let's start us off by drawing our initial arm. And since we're working with 75 degrees, I'm going to draw it here in this quadrant. And we can see that we have 75 degrees right there. And we're going to reflect this in the y-axis. So our y-axis is right here. So if we were to do so, we're going to reflect it and it comes across on this end. And we can see that we still have that reference angle of 75 degrees. But if we were looking now of our angle in standard position, we're going to still start off with our initial arm. And then coming all the way over there, we're going to take 180 minus 75 gives us our new angle. In this case, it's going to be 105 degrees. Taking a look at B, we're going to reflect the original angle in the x-axis. So once again, starting off with our initial arm, let's draw our terminal arm for 75, and we have our 75 degrees here. We're reflecting it in the x-axis, which means it's going to come down into this quadrant here. So we can see that we've got our 75 degrees. Our reference angle is going to be there as well. But if we are looking for something in standard position, we're going to start from our initial arm and come all the way back around. And we're going to now take 360 minus 75 to give us our angle in standard position. So now this is going to be 285 degrees. So coming all the way around until that purple terminal arm gives us 285 degrees. Last but not least, looking at C, we're going to reflect it in the y-axis and then the x-axis. So let me quickly draw my terminal arm. So we're going to reflect it first in the y-axis. So we're going to now come over here. And then we're going to reflect it in the x-axis. So we're going to take the blue line and we're going to reflect it down here. Now keep in mind that our reference angle for each of these, this is 75. This was still 75. And coming down here, this is still 75 degrees. So if my reference angle is 75 degrees, we know that we've gone now, and maybe I'll do this in red, starting with our initial arm, we're going 90, 180, and then 180 plus 75 is what our angle in standard position is going to be. And in this case, we have 255 degrees. So a quick little summary of what we just noticed. If we were to draw a Cartesian plane here, we can see that our angle in standard position, just our theta, is going to be whatever our reference angle is going to be. In this quadrant, and maybe what I'll do is I'll introduce the idea of different quadrants. We have quadrant 1, which starts up here, quadrant 2, 3, and then 4. We're going to review that a little bit later on as well. Then in quadrant number 2, our angle in standard position is just simply going to be 180 degrees minus your reference angle. So just to illustrate real quick, if I have my terminal arm here, we're going to come all the way up around here. We have my reference angle, and we're going to take 180 minus this angle, gives us our angle in standard position. In quadrant number 3, we have theta, our angle in standard position. It's going to be 180 plus our reference angle. And then in quadrant number 4, we have our standard position angle is going to be 360 minus our reference angle. Now, you don't necessarily need to memorize this, but these are just some observations that we can see. And you'll notice just by drawing your angles in standard position that you don't really need to memorize, that you can just simply start working with easy numbers like 90, 180, and 360. What we're going to do next is look at what we call special triangles. Now, the reason why we explore these might not become very apparent right away, but essentially the reason why we study these or learn about these is that they become the building blocks for the rest of trigonometry in high school and in university. And if we look at the angles that are given to us, 30, 60, and 45, as well as 90 degrees, they happen to mesh very well with each other. 30 and 45 being nice divisors of 90. We have 30 and 60 adding up to 90. So being able to understand these two triangles essentially are the building blocks of trigonometry for higher level courses. So starting us off here, we're going to look at the 30, 60, 90 triangle. And essentially where this comes from is we are looking at some sort of equilateral triangle with side lengths of 2. Oh, that was very messy. Side lengths of 2. So if we were to look at this triangle, we know that we would have a side length 2, 2, and 2. And what we've done here is we've split it in half. And this half right here on the left is what we are looking at down here. Let's label our 30 and 60 degree angles. So this is going to be my 30-degree angle right there. And down here in the bottom left is going to be my 60-degree angle. Now, of course, in the bottom right is going to be our 90-degree angle because we've split that equilateral triangle in half. And now we can start to label some of the sides. We can see that the hypotenuse of this right angle triangle is going to be 2. The bottom side of this triangle is simply going to be 1 because once again, we've split this equilateral triangle in half, meaning that this side right here is just going to be 1 rather than 2. And to calculate that last part of our triangle, we can simply call this x for the time being. Using our Pythagorean theorem, we know that we have a squared plus b squared is equal to c squared. And because we have the squares of our two non-hypotenuse legs is equal to our c squared, we're going to take x squared plus 1 squared is equal to 2 squared. So that means I just have x squared plus 1 is equal to 4. Let's subtract 1 from both sides. And then we're going to square root both sides so we get plus or minus the square root of 3. But because we're looking at a side length, we're going to take the positive square root. So x in this case is simply going to be, and I'll do this in green, the square root of 3. So from here we can come up with a few conclusions. Let's go ahead and write the 3 primary trig ratios. So starting off with sine, I'm going to start off with the 30 degrees here. Sine of 30 degrees is going to be my opposite side, which is 1, divided by my hypotenuse, which is 1/2. Cosine of 30 degrees, we're going to look at my adjacent side, which is root 3. And we're going to divide that by the hypotenuse, which is 2. And finally, the tangent of 30 degrees is going to be opposite over adjacent, so 1 over the square root of 3. And if you'd like, we can rationalize this as the square root of 3 over 3. Let's do the exact same thing with the 60-degree angle. So sine of 60 degrees is equal to opposite, which is square root 3, divided by my hypotenuse, which is 2. Cosine of 60 degrees is equal to my adjacent side, which is 1, divided by my hypotenuse, which is 2. And last but not least, we have tangent of 60 degrees, which is equal to my opposite over adjacent, so square root 3 over 1, which is just equal to the square root of 3. At this point, you're probably thinking, okay, cool. We have our primary trig ratios, which I understand. And the point is what? Well, there's 2 main things we can actually get out of this observation. The first thing is if we're looking at the ratios of our 3 sides here. So once again, maybe what I'll do is I'll draw another triangle just to make it a little bit neater. We can see that in a 30-60 triangle, let's say that this is 30 and this was 60. And we know that this side is 1, this side is 2, and our last side here is square root 3. We know that as a fact. Now, the application of this is, let's say, for example, we know now that, let's erase these 3 sides. Or actually, what I'll do is I'll make a completely new triangle. And the only thing that we know is that this is 60, this is 30, and we know that we have our ratios here. How does knowing these 3 side lengths or the ratios help us out? Is, let's say, for example, is if the bottom here was 3, we know automatically that the hypotenuse is always double the length of this bottom side. So if I know that this is 3, this side must be 6. And if I know that this bottom side is 1, this upright height is going to be square root 3 times as big as the bottom side. So I can confidently state that this is going to be 3 square root 3 because it's 3 times square root 3 times as big as that bottom side. If you don't believe me, we can go ahead and test it out. Let's say we only know our 2 side lengths. So we have 6 squared here. Let's pretend we don't know that. Let's call this x. We have 6 squared, or rather, let's start with 3 squared, plus x squared is equal to 6 squared. We have 9 plus x squared is equal to 36. We're going to subtract 9 from both sides. So it will be x squared is equal to 27. And then I have x is equal to the square root of 27. I can simplify this to the square root of 9 times 3, which then further simplifies into the square root of 9 times the square root of 3. And that simplifies into 3 square root 3, which we already knew. If you don't believe me, we can try it again with another triangle. Maybe I'll draw it like this. So we know once again that this is 60, this is 30, and let's say that this is 2, and this is 4, then I'm going to state that this side here is 2 square root 3, and we know that as a fact. Now, the next thing that is maybe less fun for people who are new to trig, but very fun for math teachers in particular, is what we've come up with in terms of these equivalencies here. We stated that the sine of 30 degrees is equal to 1 over 2. So 1 over 2 we know is 0.5, right? So 1 divided by 2 is 0.5. But what is sine of 30 then? Well, according to this equation, sine of 30 therefore must also be equal to 0.5, which we can see here. If we start to explore the same thing as cos of 30, we can see that cos of 30 is about 0.866, but we said it was equal to the square root of 3 divided by 2. And we can see that we have the exact same thing. So the fun part as a math teacher now is that I never have to go back to my graphing calculator and punch in cos of 30 because I automatically know that the square root of 3 over 2 is the same thing as cosine of 30. And these are what we call exact values. So we can go ahead and write that down here. We call these exact values. So once again, we can apply the same thing with sine of 60. I know that if I were to punch in sine of 60, let's go ahead and do that, sine of 60 degrees, I will end up with square root 3 over 2, just like I had previously. The use cases for these exact values aren't really apparent at this point in time, but later on when we start to talk about the unit circle, you'll see exactly where we're going with this. Let's turn our attention now to the 45, 45, 90 triangle, where we're really just looking at some sort of isosceles triangles. So isosceles triangle, which means that we have 2 equal sides. And in this particular case, we're going to say that our 2 equal sides are going to be 1 and 1, just for simplicity's sake. So starting off with our 90-degree angle here in the bottom left, that means that these 2 remaining angles are 45 and 45 degrees. A quick calculation for our hypotenuse, we have 1 squared plus 1 squared is equal to, let's call that x squared. So we have 2 is equal to x squared, so x is equal to the square root of 2, so we can go ahead and label that there. And doing the exact same thing that we did with our previous angles of 30 and 60, we can write out our three primary trig ratios. We have sine of 45 is equal to opposite over hypotenuse. So let's say we're using this bottom right one. Opposite over hypotenuse means we have 1 over square root of 2. And I'm going to rationalize this by multiplying both the top and the bottom by square root 2. So this means I have square root 2 over the square root of 4, which simplifies to just a 2. Same thing with cosine of 45. We're looking at the adjacent over the hypotenuse. So once again, 1 over square root 2, which again is rationalized as square root 2 over 2. And last but not least, tangent of 45. So tangent of 45 degrees. Add the degree sign to all of those. So tangent of 45 is equal to opposite over adjacent. So opposite over adjacent is 1 over 1, which is just 1. So once again, looking to some of our applications, we know that sine of 45 we said was equal to square root 2 over 2. If I go ahead and enter square root, or sine of 45 rather, we have 0.707. If I enter square root of 2 and I divide that by 2, you can see we get the exact same thing. So these values on the right-hand side are, once again, what we call exact values. So tan of 45, you can see is just 1, which is exactly what we had. So if you're ever asked, what is the exact value of sine of 45, you'll know that we have the square root of 2 divided by 2. At this point, you're probably thinking, well, now I have all this useless information in my head. How does this help me? Well, let's go ahead and figure that out. Starting off with our 315 degree angle here, we're going to draw it in standard position. We're going to figure out what the reference angle is, and then we start to label the lengths of this reference triangle based off of one of your special triangles. So let's start off by drawing our Cartesian plane here. And we know that 315 degrees is going to be down here in quadrant number 4. So let's go with my initial arm. My terminal arm is going to be down over here. So my angle in standard position is going to come all the way over there. And we can see now that we have our reference angle, which is going to be right there. So maybe I'll label some of these first. 315 degrees, that is my angle in standard position. And we can see here that this reference angle is simply going to be 360 minus 315, which gives us 45 degrees. So our reference angle is equal to 45 degrees. Now, using our special triangles, we can see here that if I were to highlight this, maybe I'll finish drawing the rest of my triangle here in purple, we can have this triangle right here, and I'll draw it a little bit bigger. So this is the triangle here that's formed. And since we know that this is 45 degrees, this angle right in the corner would be 90 degrees, which means that our remaining angle down here is 45. So if we were to look at our special triangles back up top, we're essentially just reflecting it and then reflecting it again. So we can see here that if I were to flip this over onto this side, we're essentially doing something like this. We're reflecting it one time so that the 90 degree angle is here. And then we're reflecting it one more time so that the 90 degree angle is in the top right hand corner. And we have our 45 and 45 here. We can see that our side lengths of 1 and 1 will be right here. So we have 1 and we have 1. And that means that our hypotenuse here would have a length of square root 2. Now, this is very significant for us because what we're going to do now is we're going to now look at the sine of 45, or not 45 rather, the sine of 315, the cosine of 315, and the tangent of 315 degrees. And we're actually going to be using our exact values that we found earlier. So we can see that we're going to deal with square root of 2 over 2. We're going to have, again, square root 2 over 2 and a 1, except notice what the signs are going to look like. If I enter in sine of 315, notice that now I have negative 7 point, or negative 0.707. Cosine of 315 remains a positive 0.707, or a positive root 2 over 2. And then finally, tangent of 315 is -1. Now, if we think about what we're doing on our Cartesian plane here, what we'll notice is if I were to ask you about this point right there, based off of what we notice in this triangle, this point, we're looking at our y values, this would actually be a -1 in order for that point to be there. Our x value, which would be this top side, would have a positive value. So what's actually happening here if we were to look for our exact values, if I were to go ahead and do this, so sine of 315, we're really looking at it in terms of our reference angle here. So we have sine of 45, in this case, is opposite. If we're looking from this side, opposite, which is -1 over hypotenuse, which is √2. And we're going to rationalize this by rewriting it as -√2 over 2, which is where that negative sign comes from if we're looking at sine of 315. Because once again, don't forget that we are starting with our angle in standard position. So starting from our initial arm, and we're coming all the way back over here. So we're using this reference angle of 45 to help us figure out what the exact value of sine of 315 should be. But now with the addition of knowing that this opposite side actually is a -1, helps us remember or understand where those negative signs are coming from. Let's do the exact same thing with 240. So let's draw a Cartesian plane. So again, with our initial arm, we're going to draw our terminal arm here in quadrant number 3. So 240, we end up somewhere, let's say about here. And we have our angle in standard position. So that's going to be 240 degrees. And then measuring our reference angle, let's do this in purple. We're going to end up with a triangle that looks just like this. And if I were to zoom into this triangle, we can see that this angle right here is the result of going 180 plus 60. So we know that this angle right here is 60 degrees. This is my right angle, my perpendicular angle, which means that this last angle has to be 30 degrees. And what you'll notice here is that we have the exact same triangle that we did up here, except once again, we are reflecting it and then flipping it one more time. So here, if I were to reflect it just like so, we're basically imagining a mirror right there. So we're flipping it onto this side. And what's happening is we're flipping it one more time in this imaginary line. So we end up with a triangle that looks something like this. And we can see here that we have my 30 degrees over here, and the 60 degrees is right there. So looking at our side lengths, and maybe I'll erase this now. Looking at our side lengths, we can see that this 1 was this bottom side right there. Maybe I'll do this in a green. So the 1 is right here, which means that the 2, and I'll do this perhaps in a yellow, the 2, our hypotenuse, is going to come right here, which means that our √3 has to be this side right there. Now it'll become a little bit more apparent as we label here. So the 1 stays right there, the 2 is right here, and the square √3 of our hypotenuse is right there as well. So if I apply that same logic down here, the 1 is going to be right there. We have 2 as our hypotenuse, and then this side that drops straight down is going to be square √3. Now, once again, we're going to look at this in terms of a reference angle. So we're looking at 60 degrees, but because we're here in this quadrant, we're now looking at this point right here. And we'll notice pretty quickly that for us to have some sort of point x, y on this portion of the Cartesian plane, the only way that this can happen is if this side that drops down this way, and maybe I'll do this in a blue, this side here has to be a negative value. So that means that this side is actually represented by negative square √3. And we can see here the same thing for this portion, I'll do this in a yellow, this length that comes out this way actually needs to be represented by -1. Now, I know a lot of you guys are probably thinking, well, you said that we can't have a negative length, and that's still true. We can't have a negative length. But what we're interpreting it as is what is the value of our x and y here? So that means if I were to come up with our point right here, this x and y value, our x is -1, and our y value is actually -√3. Now, this probably does not make a whole bunch of sense right now, but it will once we move into some more examples later on, where we talk about how the x and y values are used with our special triangles. Now, once again, looking at our standard position angle, we have 240 degrees. If I were to take the sine of 240, the cosine of 240, and the tangent of 240, we're going to be referring to our exact values using 60 degrees. So if we go back up and we look at our 60 degrees, we have √3/2, 1/2, and √3. So we can start off by writing those down. √3/2, 1/2, and √3. Now again, looking at our calculator here, we're going to punch in a few different values. Sine of 240. Sine of 240 should give us a negative value, but remember what we said here about our special triangle. Our special triangle is really just a point of reference, hence our reference angle. If we were to take the sine of 60 using our purple triangle here, the sine of 60, and I'll write that down here, sine of 60 is opposite over hypotenuse, which is going to be -√3/2. And we can see that -√3/2, -√3/2, is exactly what we have when we punch in sine of 240. So what our special triangles have allowed us to do is to start off with a point of reference, or our exact values, and then understanding how our Cartesian plane works, we can assign now values that are either positive or negative for our side lengths. So using our special triangle here, we had a reference point for which we got -√3/2. And we know for a fact that this is the same thing as sine of 240 degrees. So that's where that negative is going to come from when we put in sine of 240. So keeping that in mind, what we're going to do next is we're going to draw each of these angles in standard position, and then we're going to state the reference for each one. So starting off with 120, I'm going to draw my terminal arm here in quadrant number 2. And now my angle in standard position, I know that I have my 120 there. And my reference angle, therefore, is 60 degrees. So if I were to label my reference or label my special triangle here, I know once again that this must be 1, this is 2, and this is √3. But again, if we were looking at this in terms of some sort of point, in terms of x and y, the only way we can plot a point here is by finding out what those coordinates should be. My x value, because we're starting from the origin and we're counting this way, we said we have a length of 1. This x value is represented by -1. And the y value here is simply going to be this positive √3. So if I were to draw this or plot this as a point, I could actually label this point here -1/√3, and I'd be able to draw this triangle. As such, if we were to use this reference or the special triangle to help us figure out our exact value for each of the following, we can go ahead and state that sine of 120, we know we're looking here, opposite over hypotenuse, is simply √3/2. Cosine of 120 we know is adjacent over hypotenuse. So according to this triangle, adjacent is -1 divided by my hypotenuse, which is 2. And once again, if I were to punch in cosine of 120, we can see that we get negative 1.5, which is the same, or negative 0.5, which is the same thing as negative 1/2. And looking at tan of 120, if I were to enter this into the calculator, tan of 120 gives me negative 1.73. If we were to look at our tangent ratio for this particular triangle here, tangent of 120, we're now looking at opposite over adjacent. So opposite is root 3 divided by my adjacent side, which is negative 1. So root 3 over negative 1 is the same thing as negative square root 3. And this is not by accident. Let's go ahead, punch in tan of 120. The square root, or rather negative square root 3, just so happens to be the same thing as negative 1.73 as well. So we can see here that using our special triangles, we can find out the exact values for some of these other angles on the Cartesian plane, and we can figure out if they're positive or negative just by drawing our triangles. Let's do the same thing with 330 degrees. So starting off once again with our initial arm. So we have our initial arm here. And let's draw our terminal arm. We're here in quadrant number 4. Let's draw our angle in standard position. So we know that's 330 degrees. We know that this reference angle is going to be, our reference angle is 30 degrees. So if I were to extend this out, let's make this a little bit bigger. That is my special angle triangle, or special triangle, a 30, 60, 90 triangle. So that's my 90 degrees. And over here is my 60 degrees. And let's label our 3 sides. We know that this bottom leg of what's usually an upright triangle is going to be 1. Our hypotenuse is going to be 2. And this long side of our triangle is going to be square root 3. Now, once again, if we were to imagine a point being plotted right here as an x, y coordinate, the only way we can get this x down here is if we were looking at this side length, which is going to be square root 3. And this y value, we can see that it's going to drop straight down from there, should actually be a negative 1. So this should be a negative 1 right there. And what we'll do is I will make this a little bit bigger so we can see. So this should be negative 1. We said this was root 3 and this was 2. And we said that this was 30 degrees. So if we were looking at these in terms of exact values, we're now going to do the same thing for sine of 330. So we have opposite over hypotenuse, which is negative 1/2. Cosine of 330, which is the same thing as the cosine of 30, we have adjacent over hypotenuse, so square root of 3 over 2. And then now tangent of 330 is going to be my opposite over adjacent, so negative 1 over square root of 3. So once again, just to confirm, we have sine of 330. Let's go ahead and punch that in. And we can see once again that we did find that negative 1/2. Cosine of 330 is the same thing as root 3 over 2. And tangent of 330 is the same thing as negative 1 over root 3. Let's go ahead and do that. Negative 1 over square root of 3. And we see that we have the exact same answer. Here you can pause the video, try out the next 2 on your own, and then unpause to check your work. So now we're going to skip ahead to the cast rule. One way to remember the rule is by using the mnemonic all science teachers cheat, but because I love all the science teachers at our school, we're just going to call it the cast rule. So the cast rule essentially just tells us exactly what our trig ratio signs are going to be in each quadrant. Now to remind you guys, we start off with quadrant 1 in the top right, then 2, 3, and 4 following it. Now the cast rule in this sense, we have C, which is obviously cosine, A meaning all, S is sine, and T, which is tangent. And looking at our quadrants here, in quadrant number 1, all of our trig ratios are going to be positive. In quadrant 2, all of our sine. In quadrant number 2, only sine is positive. In quadrant 3, only tangent is positive. And in quadrant number 4, only cosine is positive. So in our chart here, we can go ahead and fill in what our positive and negative ratios are going to be. So in quadrant number 1, we can see that all of them are going to be positive, so we'll label them as such. In quadrant number 2, only sine is positive, so I'm going to label that as positive, and the other two are negative. In quadrant number 3, only tangent is positive, and the rest are negative. And finally, in quadrant number 4, only cosine is positive, and the other two are negative. Here in our example, we're trying to figure out which quadrant each terminal arm is going to lie in. If cosine is positive and sine is negative, so once again, a positive cosine means we're looking in either quadrant 1 or quadrant 4. And because we're looking to see where sine is negative, it's going to be in quadrant number 4. Same thing with the second example here. Tangent is going to be negative, so it can't be quadrant 1 or 3. So it's either 2 or 4. And sine is negative. We can see that sine is positive up here, so the only remaining answer is quadrant number 4. And in the last problem here, tangent is positive, so it's either 1 or 3. And we know that cosine is going to be positive, so it has to be quadrant number 1. So we're going to back up in the notes a little bit and talk about the unit circle. Now, the unit circle is primarily used in Math 30-1, so the next course after Math 20-1. But really what it does is it puts all of the special triangles together and helps us determine the exact values of a whole bunch of different trig ratios. Now, some of the basic information that we see here for a unit circle, we have 4 of our main points making our circle. So we start off at 0 degrees, which is at 1, 0. 90 degrees is at 0, 1. 180 is at negative 1, 0. And 270 is at 0, negative 1. And finally, we go back up to 360, which would once again be at 1, 0. Now, the reason why we call it a unit circle is because the radius of our circle is exactly 1 unit in length. So if we were looking at a triangle that looked like this, then our hypotenuse is exactly 1 unit in length. Now, going back to one of our previous pages where I talked about having a point xy here, this will make things a lot more clear as to why we kind of built things up until this point. So you can see here that we had this point on the vertex of our triangle. We're going to do the exact same thing here, except we know now that the radius is 1, which means that our hypotenuse will also be 1. So this line right there gives us a hypotenuse of 1. And because our point here is xy, our representation of x is going to be this side right there. So we know that that green line is x units long, which means that this height of the triangle is going to be y units long. So if we're looking at sine of theta, and let's go ahead and label theta right here. So that's going to be our theta. So we're looking at sine of theta. Sine of theta means we're looking at opposite over hypotenuse. So opposite is y over 1, which is just y. Cosine of theta is going to be equal to adjacent over hypotenuse, so x over 1, which means that we have x. And tangent of theta is opposite over adjacent, which is y over x. So the takeaway from all of this is understanding that your coordinates of some point on the Cartesian plane can be represented by cos theta and sine theta. Let's put this into use with our special triangles. So starting off with our 30-degree special triangle, let's go ahead and draw our triangle here. And let's make this a 30-degree triangle. We're going to do the same thing. I'll just draw my 60-degree triangle, and we'll do so just like that. We'll have this be, oops, not 30 degrees. This is going to be my 60-degree triangle. And what we're going to do is we're going to try to figure out what this representation is for this point. What will our x and y coordinate be for that triangle? And we're going to do the same thing for this second triangle. So I'll give you guys a second there to draw those. And once again, I'm just going to label our hypotenuse here as 1 because we know that our unit circle has a radius of 1, so our hypotenuse is automatically 1. Referring back to our 30, 60, 90 triangle, remember that we drew it just like this. Maybe I'll draw it up here for you guys. So we'll have our 60-degree angle. We've got the 30 here, and we know that this was 1, this was 2, and we know this was square root 3. So what will make things a little bit easier now, let's pretend that we're working with our 60-degree triangle first. So what we're doing is we're going to put our green vertex up there. So we're trying to figure out what exactly our ordered pair will be for that green point. And that depends on what the remaining lengths of our triangle are going to be. Now, remember what we said about our special triangles. They help us figure out exactly what other triangles or what other similar triangles will be because we know what the proportions will need to be. Since our hypotenuse for this particular example is 1, we know that our original was 2. So in doing so, going from 2 to 1, we are drawing a new triangle with everything being at a ratio of 1/2. So everything in this triangle down here is half the length of this original special triangle up here. That means for us, this bottom portion, instead of this having a length of 1, this now becomes a length of 1/2 in our unit circle. Or this height of our triangle, this root 3, where if we're dividing that in half, that now becomes root 3 over 2. So that means that this side is square root 3 over 2. Because again, these are similar triangles, so the proportions must be the same. We've divided all the side lengths here in our original by 2 to get the new lengths for the similar triangle in our unit circle. So based off of our observations from here, we know that our x value is the same thing as cos of theta. Cos theta is our x. And if we know that we're looking at our x value here, it's going to give us an x value of 1/2. So we can go ahead and put the 1/2 there. And for our y, it's going to be the same thing as sine theta. And we know that sine theta is going to be our y value. And our y value in this case is square root 3 over 2. So we can see that our special triangles help us construct our new triangles within the unit circle, and we can figure out our coordinates fairly quickly using our understanding of special triangles. So looking at our 30-degree angle, we're just simply going to take this and we're going to tilt it sideways. So and maybe I'll do this a little bit better. So this 60-degree angle is now over here. Our 30-degree angle is now here on the bottom left, matching us up with the unit circle. And our perpendicular angle is right down here. So we know that this side is going to be 1, our hypotenuse is 2, and this bottom side is root 3. And once again, because our triangles are similar to each other, right? Remember, similar triangles have the same ratio of sides. We can see that our hypotenuse going from 2 to 1, we're going to divide everything by 2. So I go 2 divided by 2 gives me 1. I'm going to take this 1 here on this side, and now this 1 becomes 1/2 in this triangle. This root 3 over 2 now becomes, or rather this root 3 becomes root 3 over 2. So this blue side is square root 3 over 2. And according to our observations from earlier, we know that our x and y are going to be dependent on the side lengths of this triangle. So my x in this case is root 3 over 2. And my y value was 1/2. And the last thing that we're going to do is the same exact thing with our 45, 45, 90 triangle. So our 45, 45 triangle looked like this. So we had 45, 45, and our two side lengths were 1 and 1, and our hypotenuse was square root 2. If I were to draw a circle here, this won't be pretty. So I'm going to draw that circle just like that. And we're going to have our 45-degree angle right here. So that's my 45-degree angle. We're now going to use our special triangle as a point of reference for this red triangle. So imagine if we just essentially flipped everything around, we reflected it. So now that's my 45, that's my 45, and we have the 90-degree there. But because our hypotenuse is now a side length of 1, and we know that the original was square root of 2, we're going to divide everything by the square root of 2. So this square root of 2 is now square root 2 divided by square root 2, which is now equal to 1. So that means that I'm going to divide everything in this triangle by square root 2 to ensure that I have the same proportions. So this 1 now going divided by square root 2, and same thing with this one. I'm going to divide that by square root of 2. But because we like to rationalize our denominators, and it helps us with the trick later on, I'm going to rationalize it and rewrite this as square root 2 over 2 for both of these. So square root 2 over 2. So for us, we know that this side is square root 2 over 2, and this side is square root 2 over 2, which means that this point right up here is represented by the ordered pair root 2 over 2 and root 2 over 2. So what exactly does that leave us with in terms of our unit circle? Well, looking at our unit circle, we're going to first draw or label our 4 original points. So we know that this was 1, 0, this was 0, 1, this was -1 and 0, so -1, 0, and then we have 0, -1. And I'm going to fill in all of our angles here. So this first point would be our 30-degree angle. So we have our 30-degree angle. This would be our 45-degree angle. This is our 60-degree angle. And we are going to simply take all of the different ordered pairs that we found represented each of these 3 points. So going back for 30 degrees, we can see that our 30-degree triangle yielded an ordered pair of root 3 over 2 and 1/2. So let's go ahead and write that down. So root 3 over 2, root 3 over 2 and 1/2. We're going to do the same thing for the 45-degree angle. So we're going to go back to our 45-degree triangle down here, and we had an ordered pair of root 2 over 2 and root 2 over 2. So let's go ahead and fill that in. So root 2 over 2 and root 2 over 2. And last but not least, we have our 60-degree angle, which we're going to refer to this ordered pair. We have 1/2 and root 3 over 2. So 1/2, 1/2, and root 3 over 2. And you're probably thinking, wait, do I have to memorize this? And chances are your teacher is going to expect you to memorize this. And you're thinking, oh my goodness, how will I ever remember all of these fractions, all of these square roots and whatnot? It's really as simple as 1, 2, 3. The reason I say that is if you can count from 0 to 3, you'll be absolutely fine. Starting off with our point up here, our 0, 1, remember we're starting off with our x values. Notice how we start with the 0 here. Going clockwise, we go 0, 1, 2, 3, and you'll notice that everything up here is square rooted. So we can think of this as square root 1, which is 1, square root 2, and then square root 3. Coming back the opposite direction, I'm going to start down here from 0, and we'll notice that we have 1, 2, and 3. And once again, we're going to put square root signs over the 3 and the 2. And the last thing that you need to keep in mind is that we're dividing everything by 2. So everything here is divided by 2. So if you can remember that, you've memorized this first quadrant. Now, if you recall what we talked about in terms of our cast rule, we started with CAST, just like so. This can help us label the rest of our unit circle as long as we understand how the cast rule helps us out. Remember on the previous page, we said that our coordinate pairing or ordered pair was cos theta, sine theta. So how does this help us out? You'll see here in quadrant number 2 that all of your sine ratios are going to be positive, but everything else is going to be negative. Our work from earlier in the notes helps prepare us for just reflecting all of these values onto the other side. So this 60 degrees is the same thing as the 60 degrees over here with our reference angle. Remember, this 60 degrees represents this 60 degrees coming this way. That's our reference angle. So I'm going to go ahead and start off there. We're going to use our little 1, 2, 3 trick here. So starting from 0, we have 1 over 2. Over here, we have square root 2 over 2. And then finally, we have square root 3 over 2. Going the opposite direction, we start from 0. Over here, we have 1 over 2, square root 2 over 2. And then finally, square root 3 over 2. Now remember what we said about sine being positive. Our sine of theta is always going to be our x or our y values rather. So that means all of our values in the y position are going to be positive, so we don't need to change anything about them. But that means that everything else is going to be negative, particularly our cosine. Our cosine in quadrant number 2 is going to be negative. So this needs to be negative 1/2, negative root 2 over 2, and negative root 3 over 2. Once we've labeled those, we can go ahead and write in our new angles in standard position. So this angle right here is going to be 90 plus 30 degrees. So this is going to be 120. Over here, this is going to be 135. And finally, we can think of this angle here. This is our reference angle of 30. This angle is going to be 180 minus 30, which is 150 degrees. Let's start with quadrant number 3. We can start with our y value this time. So in each ordered pair, let's go ahead and label these. So we have 1, 2, and 3. So we're going to start from 0, but now we're looking at the, we can start off with the y values first. So we go 0, 1 over 2. 2 over 2, which is really square root 2 over 2. And finally, square root 3 over 2. And then coming back the opposite direction, we're starting again from 0, but now in the x position, we have 0, 1 over 2, square root 2 over 2, and finally, square root 3 over 2. Now, because we're working in this quadrant here, in quadrant number 3, only our tangent ratio is positive, which means that cosine and sine are both negative in this quadrant. So what we're going to do is we're going to put a negative in front of each value here. So all of these trig ratios are going to be negative in this quadrant. And then once we've labeled all of our sines, we can go ahead and put in our angles in standard position. So we can think of this one right here. Once again, this is a reference angle of 30 degrees. So this one is going to be 180 plus 30. So that'll be 210. This one is 180 plus 45. So that's 225. And then 180 plus 60, which is 240 degrees. And while we're here, we can go ahead and draw in our 90, 180, and 270 degrees. And then now to label our final quadrant here, we've got 1, 2, and 3 ordered pairs. So we're going to start from our x coordinate. We're going to go 0, 1, 2, and 3. Remember that we're dividing everything by 2. And we're putting square roots on everything. So square root of 1 is just 1. And then coming back the opposite way, starting from 0, we're going to go 1, 2, 3, divide everything by 2, and then put a square root above everything on the numerator. And now in terms of looking at our signs, if they're positive or negative, we can see here that only cosine is going to be positive, which means that sine is negative. So sine is all of our y values. So now we have negative 1/2, negative root 2 over 2, and negative root 3 over 2. And we can label the rest of our angles in standard position. So we can think of this angle as 360 minus 30. So that gives me 330. This is 360 minus 45, which is 315. And then finally, this is 360 minus 60, which is 300 degrees. So now we've completed our unit circle, and hopefully using that 1, 2, 3 trick, it helps you figure out how to memorize or at least understand how to come up with all of these ordered pairs with relative ease. And then using our cast rule, we can figure out which of our ratios are going to be positive or negative. Now down here, we're going to use the unit circle to find the exact value of each of these. So looking at sine of 60. So sine of 60, we're looking at this ordered pair, and our sine of theta is our y value. So that just means we're looking at square root of 3 over 2. Cosine of 225, we're looking down here at 225. Cosine is our x value. So now we can write that the exact value of cosine of 225 is negative root 2 over 2. And once again, if we go into our calculator, let's go ahead and bring that up on the screen here. So on our calculator, if I type in cos of 225, we'll end up with negative 0.707. And if I put in negative square root 2 over 2, you'll notice that we end up getting the exact same thing. Moving on to tangent of 150 degrees, we're going to come up here, and we know that the tangent of some sort of angle is going to always be y over x. So we're thinking of y over x. That means we're looking at 1 over 2 divided by negative root 3 over 2. And when we're dividing two fractions, it just means we're going to multiply the first fraction by the reciprocal of the second fraction. So this will be 2 over negative root 3, and the 2's will factor out, which means we have 1 or negative 1 over root 3. So negative 1 over root 3 is what we end up with. Finally, we have the cosine of 270. So cosine of 270 is right down here, and we know that it's going to be 0. So for this bottom row of questions, this is where understanding the cast rule really helps us out. We have sine of theta is equal to root 3 over 2, and we're going to need to find theta when the sine of theta is root 3 over 2. Since we know that sine is positive in two quadrants, particularly, or more specifically in quadrants 1 and 2, we're looking at two places where we have that ratio of root 3 over 2. We can see that we have one right here. Let me go ahead and highlight this. Sine is root 3 over 2 right here at 120. And it's also root 3 over 2 at 60 degrees. So therefore, we actually have two answers for this question. So sine theta is equal to root 3 over 2 when theta is equal to 60 degrees, or when theta is equal to 120 degrees. We'll do one more example here. We're looking for when cosine of theta has a ratio of negative 1/2. Cosine is going to be negative in quadrants 2 and 3. So you can see here in quadrant 2 and quadrant 3, cosine will be negative. And if you think about it, it makes sense. Cosine, otherwise known as our x values are going to only be negative in quadrants 2 and 3. So that means we're looking for when we are looking, so that means we're looking for that negative 1/2 in our unit circle. And we see it in two places. Once again, we see it here at 120, and we also see it down here at 240. So cos of theta is equal to negative 1/2 when theta is equal to 120 degrees, or when theta is equal to 240 degrees. You can pause the video here and try out these next two problems on your own. What we're going to do now is put together everything that we've done so far and be able to figure out the trig ratios of any angle that's given to you. In our first question, we're told that the point -15, -8 lies on the terminal arm of an angle. We're going to use this information to write down each of the primary trig ratios. Let's go ahead and draw our terminal arm here. So starting off with our plane and then drawing our terminal arm. Now it's going to be in this quadrant here, -15, -8. And we know that we have theta, which would be right there. We don't actually care about what theta is in this example. We just want to know what the different side lengths are. So we're going to have this side length in green, and we're going to have this side length of our triangle in blue. And what's going to happen is we know that this right here is -15, -8. So that means we can actually label the different sides of our triangle, particularly in the green. The green here, because we know that this point is at -8, this has to be -8. Now again, remember that lengths aren't necessarily negative. We're just using this negative to represent, again, the quadrant that we're in. Our blue side length is now going to be represented by that -15. So that -15 goes there. And the only thing left to do is for us to figure out what the radius is for this, this red line. So we can use the Pythagorean theorem to help us out. We know that we have -8 squared plus -15 squared is equal to r squared. We have 289 because we have 64 plus 225 gives us 289. That's equal to r squared. We know that we're going to take the square root of both sides, so plus or minus 289, but because we're working with a length, we want to just use the positive side length. So square root of 289, which ends up being 17 on the dot. So the reason why we've chosen to label these as negative lengths, despite the fact that lengths should be positive, is that when we're writing our trig ratios, we want to be able to see what our exact values are. And this takes into account whether or not our ratios are going to be positive or negative according to the cast rule. So starting off with sine of theta, and remember theta is going to be really our reference angle. So not our theta in standard position. So we're going to use this theta. So sine theta is going to be opposite over hypotenuse. So in this case, and let's replace this with a 17. So opposite is -8 over my hypotenuse, which is 17. Cosine of theta is adjacent over hypotenuse, so adjacent, which is -15. Let's make that -15 over my hypotenuse, which is 17. And then last but not least is tangent of theta, which is the same thing as opposite over adjacent, so -8 over 15. And when you divide two negatives, we end up with a positive. So we have positive 8 over 15. Here you can pause the video and try out this next example on your own. So in these next two examples, we're given some of the ratios and where the angle is going to be, but we need to actually figure out what the side lengths are depending on the information that we're given. So here we have an angle in quadrant 3 and tan of theta is 1 over 4. So what's going to happen is we'll first of all draw our angle. So we're looking at quadrant number 3. So let's go ahead and put our angle here in quadrant number 3. And we know that our reference angle is going to look just like this. And because we know that tangent is going to be 1 over 4, so we know that our reference angle is going to be right here. And tangent is opposite. So tangent of theta is opposite over adjacent. And because we're looking at opposite over adjacent, we know opposite has to be 1 and the adjacent has to be 4. Looking from this reference angle, that means that this side has to be 1 and our adjacent has to be 4. But because we're in this quadrant quadrant 3 rather, we know that this value has to be -1, and this value here has to be -4. So we can go ahead and actually figure out the radius or our hypotenuse using those two values. And then we're going to, from there, figure out what our trig ratios are going to be. So let's go ahead and figure out what r is. We have -1 squared plus -4 squared is equal to r squared. And now we have 17 is equal to r squared, which means that r is equal to the square root of 17. This means for us that our sine of theta is opposite over hypotenuse. So opposite is -1. And we said that our hypotenuse was square root 17. So -1 over square root 17. And then we have cosine of theta is adjacent, which is -4 over my hypotenuse, which is square root 17. Now, once again, if we refer back to our cast rule, CAST, we can see here that in quadrant number 3, tangent is positive, which is true. We know that sine and cosine have to be negative, which we know is also true from what we have gathered. In this next example, we have cosine of alpha is equal to -2/3, and tangent of alpha is positive. So let's find the exact value of sine of alpha. So from the information that we're given here, we know cosine is negative and tangent is positive. Let's go ahead and use our cast rule. So we have C, A, S, and T. So looking here, cosine is going to be negative and tangent is positive. So tangent is only positive here and here, but cosine is negative in quadrant number 3. So from these two pieces of information, we know that we're talking about quadrant number 3. So that's where we're going to draw our terminal arm and then figure out what sine of alpha is going to be. So starting in quadrant number 3, let's go ahead and draw our terminal arm. Let's make our triangle here. Remember, always with the closest x-axis. I've seen a lot of students go towards the y-axis, so just make sure that you are aware of that. So our theta is going to be in this corner. Since we have cosine is -2/3, what that's going to look like is we know that we have adjacent is going to be my -2, and my hypotenuse is going to be 3. So in this case, we know that our hypotenuse or our radius is 3, and our adjacent side is -2. The only thing left that we need to figure out is our y value, which is right here. So we can quickly figure that out using Pythagorean theorem. We have y squared plus -2 squared is equal to 3 squared. So we have y squared plus 4 is equal to 9. Y squared is equal to 5. And from here, we get y is equal to the square root of 5. But because we are in quadrant number 3, we're going to put that negative in front there because any value of sine or y here is going to be negative. So that means that for us, sine of theta is equal to opposite over hypotenuse. So my opposite was -√5 over my hypotenuse, which is 3. Now we're going to take a quick little detour to talk about quadrantal angles. I know it sounds really fancy, but it's really nothing too bad. If we look at our 4 points that lie directly on an x or y axis, so once again, we have this point right here. This would be 1, 0. This is 0, 1. This is -1, 0. And this is 0, -1. We know that this starts at 0 degrees. This is 90 degrees, 180 degrees, and then 270, and then we go all the way back to 360. If we're looking at our trig ratios, and we say we're looking at sine of beta, remember sine of beta represents our y value. What is our y value when we're looking at 90 degrees? At 90 degrees, it's going to be 1. What's our y value at 180? It's going to be 0. And our y value at 270 is going to be -1. And finally, back at 360, if we make a full circle, we are back at 0. Looking at cos of beta, remember that's going to be determined by our x value of each ordered pair. So at 90 degrees, we are at 0. At 180, we're at -1. At 270, we're at 0. and then back to 360, we are at positive 1. If we're looking at tangent of beta, remember tangent of beta is y over x. So let's clean that up, y over x. So at 90 degrees, we are going y, which is 1, over x, which is 0. So 1 over 0 is undefined. Maybe I'll undefined. At 180, we have 0 divided by -1, which is 0. At 270, once again, we have -1 over 0, which is -1 over 0, which is undefined. And finally, at 360, we have 0 divided by 1, which is 0. So the last thing that we're going to do in this outcome is to start putting together equations with sine, cosine, and tan, and to actually solve equations that involve trig functions. So for these problems, you're given a specific trig ratio, and you're going to figure out what the solutions are for each one of these. And there's going to be 2 of them for each one. Now, depending on how you want to solve these, there's different ways to approach this type of problem. So I'll give you guys a few suggestions. The first one would be to just have an idea of what that unit circle is going to look like in your head. So again, typically we're just going to isolate for quadrant number 1. If you know what quadrant number 1 looks like, then you can simply just reflect and use the cast rule for the other 3 quadrants. So what I mean by that is, let's go ahead and do this. We've got our first angle, second angle, and our third angle. And we know that this is going to be 30 degrees, 45 degrees, and then finally 60 degrees. So the way that I want to look at this, this first quadrant, so again, just to iterate that this is quadrant number 1, we're going to have our ordered pairs here. So let's put our ordered pairs. We got 1, 2, and 3. So remember that everything is always divided by 2, and we're always going to put a square root on the top, except for the 1. So what that's going to look like is we're starting off from 1, 0, and we're ending off at 0, 1. So starting off with our x's, we go 0, 1, 2, 3. And then again, from the opposite side, we have 1, 2, 3. And let's go ahead and divide all of these by 2. So they're all divided by 2, and a little messy here. They're all divided by 2, and we're going to put a square root on top of all of these. So in an ideal world, this would be a little neater, but we're going to make do with what we have here. So looking at our cosine of alpha here, we have square root 3 over 2. So we know it's going to be positive. So according to the cast rule, cosine is going to be positive in these 2 quadrants, quadrants number 1 and quadrant number 2. Because we're looking at the 30-degree reference angle, so our reference angle is going to be 30 degrees. We're going to first have our first answer of alpha being 30 degrees, and that's an awful alpha there. So alpha is equal to 30 degrees. Or we also have 360 minus 30, because we know that we need 30 degrees coming this way. So that's going to be 360 minus 30 gives us 330 degrees. The second way that we can do this is by simply looking for our angle using our calculator. So popping our calculator up onto the screen here, we're going to take the inverse cosine, so second cos, the inverse cosine of the ratio that we have, so root 3 over 2. And we can see here that it's going to be 30 degrees. And once we get that 30 degrees, if you can't remember anything from your unit circle, you can cheat a little bit and use your calculator to help you figure out what that reference angle is going to be. You're still going to need that cast rule to help you figure out which quadrant your angle is going to be in, but at least it saves you an extra step of memorizing or remembering where on your unit circle you are. So for the second one, in terms of tangent, we can just go ahead and go inverse tangent of second tangent of -1 over square root of 3. And we end up with -30 degrees. We're just going to ignore the negative. We're going to pretend that we're working in quadrant number 1. So our reference angle is 30 degrees. And because we're looking at tangent, we know that tangent is only going to be positive. So we have CAST. Tangent is negative, rather, in quadrants 4 and quadrant number 2. So our reference angle is 30 degrees. So that means I have two answers. So we have 30 degrees coming up this way. So this is going to be 180 minus 30 gives us 150 degrees. And the second potential answer, because we're working in quadrant number 4 now, we have our terminal arm there and our reference angle is there. So this will be 360 minus 30. So that means that my second answer is 330 degrees. Here you can pause the video and try out the next two on your own. Now we're going to work with some approximate values. Sometimes we don't get exact values, such as the above there where we have root 3 over 2 or negative 1/2. Instead, we're going to get some decimals, which we can use to help us figure out the ratio of some sort of trig ratio, and from there work backwards to figure out what the corresponding angle is. In order to do so, we're going to look for the reference angle, and we're going to first look for beta. So beta is equal to the inverse cosine of 0.123. And then from there, when I put that into our calculator, we end up getting, let's go ahead and see, inverse cosine of 0.123. And we end up getting about 83 degrees. So beta is equal to 83 degrees. So that means that this is my reference angle. So since that's my reference angle, we see that cosine is positive. So cosine is positive in quadrants number 1 and quadrant number 4. So what we're going to do now is we're going to draw a reference angle of 83 degrees. So we have 83 degrees, which is probably right about there. So our first angle is 83 degrees. And our second possible angle, let's draw again 83 degrees down here. We have 360 minus 83, which ends up giving us 277 degrees. For the next question, we have sine of beta is equal to negative 0.217. So what a lot of people are going to end up doing is they'll put an inverse inverse sine of negative 0.217, and they'll be a little bit confused about that negative. Now, we can simply ignore that negative, or we can just pretend that we are working with a positive here. Now, what that negative represents is the specific quadrants that we're going to be in. So again, we can also just pretend that we're working with the positive angle here, which once again is our reference angle. So starting us off, we have beta is simply equal to the inverse sine of, you can put negative, or let's go with a 0. So from here, we have beta is equal to the inverse sine of 0.217. Once again, I don't need to put that negative in because this negative tells us that sine is going to be in quadrants 3 and quadrant number 4. And then once we plug that into our calculator, we ended up getting 13 degrees. So let's draw our quadrants here. And since our reference angle is 13 degrees here in quadrant number 3, that's my reference angle. And we have 180 plus 13 gives us 193 degrees as my first answer. And then for my second answer, I'm in quadrant number 4. There's my 13 degrees. And I have 360 minus 13, which gives us 347 degrees. For this last question here, you can try this out on your own by pausing the video and then unpause once you're done to check your answer. That brings us to the end of today's video. Hopefully you learned a thing or two about angles and standard position. If you have any questions or comments, feel free to leave them down below. Thanks again for watching, and I'll see you in the next video.